Hi friends, welcome back to our channel Physics Tutorial. In the last class we had discussed the dielectrics and polarization, right? And we had just started the introduction of capacitors and capacitance. Now we are going to continue with that capacitors and the parallel plate capacitor and effect of dielectrics in capacitors like that. Okay, so if you like the video, please like, share and subscribe. Can we move to the video? Now we can discuss the principle of a capacitor. Some points you should understand about capacitor. So here we know that the capacitor is here we can see two conductors. That means here plus Q charge is here and this is minus Q charge, and they are separated by an insulator. Right. So here the air is there in between. That means that will act as an insulator. So this system, only these two here plus Q and minus Q, the potentials are V1 and V2. So this system will act as a capacitor, and we have to know that if the charge on the capacitor or the potential on the capacitor increases, what will happen to the electric field inside this? As the potential increases, the electric field also will increase, right? And when the electric field increases, what will happen is that here it will have a tendency to ionize the molecules nearby that. So suppose here we have an electric field and it ionizes the electrons and protons which are near to this, so that positive charges will attract the negative charges near to that ions, and the negative charges also will attract the positive charges. That means when the electric field becomes very high, that will ionize the nearby molecules and that will attract the opposite charges and will neutralize. Clear? So what happens is that it will not be able to charge again because we are using this capacitor for charging, right? So we have to store the energy in capacitor. So after increasing the electric field a maximum value, we will not be able to charge the capacitor anymore. Okay, so we have to find a method of decreasing the potential and store maximum energy. So that is our aim in capacitors. Now we have told that when the electric field is high, that will ionize the nearby ions and that will neutralize the charge on the plates, right? So that is called electric breakdown. So after electric breakdown, even if we charge the capacitors, that will not be able to charge it again. Okay, so this is electric breakdown. That point you have to remember. And one more thing is there, because dielectric strength. Dielectric strength means that is the maximum EMF that a dielectric medium can withstand without breakdown is called dielectric strength. That means suppose here we are taking the air as the dielectric medium and it has a value of 3 into 10 raised to 6 volt per meter. That is the dielectric strength of air. Okay, and if we are doing that experiment here and if we increase the value of dielectric strength more than this, or if the strength of the means electric field becomes more than this value, it will not be able to charge it again. Clear? So that is the dielectric strength. That means the maximum EMF that a dielectric medium can withstand without breakdown is called dielectric strength. Okay, so that is 3 into 10 raised to 6 volt per meter for air. In the case of air, the value is like this. And now we have to do one thing, that means the principle of capacitor that we have to understand. So here the charges are distributed like this, and now we can see what we have to do for reducing the electric breakdown. Okay, so for that here our aim is to decrease the potential, because we have to decrease the value of potential and then we can store more energy. And for that, what we have to do, that is the principle of a capacitor. So for that, first of all, we will take a charged conductor. Only this conductor we are taking. Here we can see that positively charged plate is taken here. Okay, and now we can take another conductor here and it is not charged. First of all, it was not charged, and only a conductor we are taking here and we are placing this B near to A. So this is positively charged and this is chargeless. Then what will happen? Here due to induction, the charges will be produced in this B. okay, in conductor B, then we can reduce the charge from A. That means the potential of A will be decreased, because here the potential will be VA minus VB, the difference between the potentials of these A and B. And here we are earthing this, so the rest of the charges will be released like this. Okay, so this is the principle of a capacitor. So instead of using one plate, here we are using two plates, and the second one plate is charged conductor and the second plate is uncharged, and this is a conductor. We are just keeping near to this first conductor, and then what will happen here, this charges will be induced in the second, and then the rest of the charges will be going to earth. That means here we can earth. Then in such a way we can reduce the value of potential. So if the value of potential is reduced, means it will be easy to charge it again, then the electric field will be very less, and then due to that we will be able to store more energy in the case of capacitor. So that is the principle of a capacitor. That means here VA minus VB only will be coming as the potential. Clear? So this is the principle of a capacitor. Here we are going to calculate the capacitance of a parallel plate capacitor. So we can consider a parallel plate capacitor, and we are going to calculate the equation for capacitance of parallel plate capacitor. So this is very important topic, and that derivation also you should understand. Okay, if we understand and study, that will be very easy. Now here we consider a parallel plate of capacitors. Here we can see two plates. This is positively charged, this is plus Q, and this is minus Q. Two plates are taken here, and here we can divide these two plates into three regions. Right, here we can take as the first region that you can take. Okay, so here we are taking, suppose this is first region, this is second region, and this is third region, and here the surface charge density of this plus charge is plus sigma, and the surface charge density of this minus plate is minus sigma, and the area of cross section of this plate, these two plates are A. Clear? And the distance of separation between the two plates can be taken as small letter d. And now we have to find the capacitance of this capacitor, parallel plate capacitor. So first of all, we have to find the electric field. So we have divided this into three regions, right? So in each region, what will be the electric field? That means the magnitude of electric field that we are going to find. Now, we know that if you are placing a source charge as positive, that electric field will be moving away from the positive charge. That we have already studied, right? In the case of positive charges, the electric field will be away from the positive charges, and if you are taking negative charges, then what will happen? That will be just reverse, right? So that will be, the electric field will be towards the negative charge. So that you have to keep in your mind, and then we can find the electric field in these three regions. Just understand that, then it will be very easy. So here, first of all, here we can see, due to this positive charge, that means due to this plus charges in this plate, what will be the direction of electric fields? Here we know that this is positive charge, means the direction will be away from this. Here, can you see? This is away from this, means this will be the electric field. Clear? And in this region, what will happen? Here, this is positive charge, right? So this will be away from this. And in this region also, due to this positive charge, we are finding the electric field direction that will be away from this. So that will be also coming downwards. Clear? So these three are the directions of this positive charges. Clear? So here we can see that this will be away. This is from positive charge moving away from positive charge. This is also moving from away from positive charge. This is also moving away. Clear? And in this, here we can see that this is the negative plate. Right. So, due to negative charge, the electric field will be moving towards this. So, we can start from here. So, here what happens? This is negative charge. So, the field will be towards the negative charge. Okay. So, the direction is coming like this. This is electric field. And in this region, what will happen? This is negative. So, this will be coming towards negative. Clear? This is coming towards negative. And in the third region, in this region, what will happen? Here is the negative, so this will be coming downwards. So all the directions of electric field is shown here, and we have already studied in the first chapter that the value of electric field in this region will be sigma by 2 epsilon 0, because here we can see these two plates are divided into three regions, right? So in such a case the electric field will be, that means sigma by 2 epsilon 0. So here we have sigma by 2 epsilon 0. So all these values will be sigma by 2 epsilon 0. Now we have to find the electric field in region 1. So what about region 1? Here we have the electric field in upward direction, and here it is downward. So what will be the total field? This is sigma by 2 epsilon 0, and this is downwards, means that is negative. Right, so that is equivalent opposite, so that will get cancelled and the total field will be 0. So in region 1 there is no electric field. And what about second region? Here we can see this is coming downwards. Okay, this electric field is sigma by 2 epsilon 0 plus here this is also in the same direction. So what will happen? Sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, that will be equal to sigma by epsilon 0. That means half plus half, that is 1. So sigma by epsilon 0 is the electric field in this region, in the central region, okay, region 2. And what about region 3? Here we have, yes, one is downwards and here this electric field is upwards. That is again equal and opposite. So what will happen here? Again the electric field will be sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, that is equal to 0. So here we can see that in region 1 and 3 the total electric field is 0. Right, and only in region 2 the electric field is there, and that value is sigma by epsilon 0. Now we have electric field, and now we have to find the capacitance of a parallel plate capacitor. So how we can find the capacitance of this parallel plate? So for that, C is equal to Q by V is there. Right, so we have to find C is equal to Q by V. Charge is already there. We have to find the equation for V, potential. So how we will find the equation for potential? We have the equation for electric field as E is equal to sigma by epsilon 0, that we have found now. Now we have an equation connecting electric field and potential, right? That is V is equal to E into D. V is equal to E into D means here we can find electric potential. So E is sigma by epsilon 0. So that means V is equal to E into D, that will be equal to sigma by epsilon 0 into D, because we are substituting the equation for electric field. And we know that sigma is the surface charge density, and that equation is sigma is equal to Q by A. That we have already studied in the last chapter. So sigma will be equal to Q by A, right? So we can substitute that also. So V will be equal to Q by A, that means sigma by epsilon 0 is there into D. So into D by epsilon 0. Here we are just substituting for sigma, that is Q by A, then D by epsilon 0. And now we have V. Then we can find capacitance, right? So C is equal to Q by V. So here we can substitute the equation for V. Then what we will get? Q divided by V is QD divided by A epsilon 0. Okay, so Q divided by QD divided by A epsilon 0 means this Q and Q will get cancelled. Then what is remaining here? Epsilon 0 A divided by D. Right, so this will go upwards. So we can write it as C is equal to epsilon 0 A by D. That is the equation for parallel plate capacitor. The capacitance of a parallel plate capacitor is C is equal to epsilon 0 A by D. That is very important equation that you have to remember. So what we have done here is, I will just have a quick review. So here we are taking two parallel plates and we divide the region into three. Right, and first of all we have to find the electric field in this. The distance of separation is D, and plus sigma and minus sigma are the surface charge densities, and A is the area of cross section of the plates. And in region 1 means 1, 2 and 3 are there due to positive charge. You should understand that all the electric field will be away from the positive charge. So this will be moving away. So here also this is moving away from this. And in the case of negative charges, the field will be moving towards negative charge. So here negative is there means this will be moving upwards near to negative charge, and here also it is coming near to negative charge here also. Then in region 1 and 3, what what happens? The electric field will be cancelled because these are equal and opposite. Only in region 2 the electric field will be there, that is sigma by epsilon 0. Then we can find the capacitance. So E is equal to sigma by epsilon 0. Now we can use the equation V is equal to E into D for finding potential. So E is equal to sigma by epsilon 0, that value we can substitute that into D. Then sigma is equal to Q by A, that is the surface charge density. Then that also we can substitute. Then equation becomes QD by A epsilon 0. Then C will be equal to Q by V. So we will get it as C is equal to epsilon 0 A by D. Clear? Now from the equation of capacitance we can understand that the factors on which the capacitance of a parallel plate capacitor depends. What will be the factors? Here area is there, then the distance is there, then epsilon 0. So we can see that it depends on the size and shape, then also the medium. Okay, it depends on the size, that means the size area, it depends, then the distance, so size, shape and the medium. That means epsilon 0 means, how we are writing epsilon 0 here, because this medium is taken as the air. Okay, that is why we are taking the value of epsilon 0 here, otherwise that will be epsilon, right? So these three factors are the depending factors on capacitance of a parallel plate capacitor. That means the shape, size and the medium. Clear? Now we are going to discuss the effect of dielectric on a capacitance. So here we have a capacitor, that means here positive charges are there and this is negative charges, and here the surface charge densities are plus sigma and here this is minus sigma, and the distance between these two plates are D and the area of cross section is capital A. Now first of all we can consider this as air. In between the plates only air is there, and then we can find the capacitance. Then we will replace this air with an dielectric. Okay, so dielectric slab we will place in between these two, and then we can see what difference is happening there. Okay, first of all we are considering only air is there, nothing will be here, only the air will be filled with this place, okay, in between the plates. Now what will be the electric field in between this? So that we have discussed in the last topic, right? So that was E air is equal to sigma by epsilon 0. So only in this region, that means sigma by epsilon 0 will be there, and that value can be used to find the electric potential. So E air into distance, that is V, electric potential. So what we will get? E is equal to sigma by epsilon 0 into D. So E, that means sigma D by epsilon 0 we will get, and instead of sigma, sigma is the surface charge density, so we can write it as Q by A. So sigma will be equal to Q by A into D by epsilon 0. So only we are using the equation V is equal to E into D. So here we are considering only air, means we are just giving the suffix A, E air. Okay, now QD by A epsilon 0 we are getting. Now we have to find capacitance. So C will be equal to Q by V. Then we can substitute the equation. So what we will get? Q by V is this one, QD by A epsilon 0. Then what we will get here? C air will be equal to epsilon 0 A by D, because Q and Q will get cancelled. That we have already discussed in the case of air. Right. Now suppose we are placing a dielectric slab in between this. Then what will happen? Then it will be polarized. Right. Here we can see this is the dielectric slab here. And then due to polarization, the surface charge densities becomes polarized charge densities. That means here this is the electric field of air. Okay, E air we can write here. This is the direction of electric field. And here in the positive charges will be moving opposite to the direction of field, right? So this positive charges, this is the direction here, and the positive charges will be moving opposite to the direction of field, and negative charges will be moving in the same direction of field. Then here we can see another set of charges. That means here positive means this positive will be formed here, and here negative, this will be move to this position. So here another set of charges will be formed in these two ends. That means this slab is polarized. So we can say that this minus sigma p and plus sigma p are the polarized charge density. So only due to this polarization this happens here. So minus sigma p and plus sigma p will be there. Okay. Now again we have to find the equation for capacitance. So we know that here we have electric field in this direction, and due to this dielectric, the direction of electric field will be like this, in the opposite direction. Okay, so these two will get cancelled, means that will be decreased, right? The electric field will be decreased because this E air minus E dielectric will be the total value of electric field in this region. So we can write E is equal to, that is the electric field in this region is equal to E air minus E dielectric. Okay, now we have to find the equation for dielectric. So how we can find? Here we know that in air, what was the equation for electric field? That was sigma by epsilon 0, because in epsilon means air, the value of epsilon 0 means that that was in free space, right? So in the case of dielectric, this epsilon 0 will be equal to epsilon, right? So that we have to replace. So that will be equal to ED is equal to sigma by epsilon, but we know that epsilon by epsilon 0 is equal to K. Right, so then what will be epsilon? Epsilon is equal to epsilon 0 into K. We can cross multiply. So epsilon 0 into K. So here instead of epsilon, we can write epsilon 0 K. Then what will be the equation of electric field in dielectric? ED is equal to sigma by epsilon 0 K. So here instead of epsilon, we are writing epsilon 0 K. Now what will be V? That is electric potential. Electric potential is V is equal to ED. The same equation we are using, ED. That means this is the dielectric electric field into D, distance. So here we can substitute the equation, sigma by epsilon 0 K into D. Right. Then instead of sigma, that is the surface charge density. Right. Instead of sigma, what we can write? Q by A. So Q by A, then D by epsilon 0 K. Now we have V. Then what about C, capacitance? How we can find capacitance? That will be equal to Q by V, right? So Q by V is QD divided by A epsilon 0 K. So that value we are substituting here. So what we will get, this Q and Q will get cancelled. Then the remaining equation is capacitance of dielectric, that is equal to epsilon 0 A, that means A epsilon 0 K by D. So this is the equation, this is the final equation, A epsilon 0 K by D. That is the effect of dielectric on capacitance. Right, now we can have a quick review. Here what we are doing, first of all we are considering two plates, and here air only was there in between. Alright, in such a case we have calculated the equation of capacitance. Capacitance means Q by V. Then V we found by using the equation E into D. Here we are just substituting just like last case, and we are getting the equation of C air as epsilon 0 A by D. And then if we replace this air with a dielectric slab, what happens here? This will be polarized. So here we can see sigma P and plus sigma P and minus sigma P as the polarized charge densities, and these charges will be polarized to these two directions, right? And this total electric field will be reduced in this case. So E will be equal to E air minus E dielectric. And then we can find the equation for capacitance, that is ED is equal to sigma by epsilon 0 K, because epsilon 0 can be replaced with epsilon. That equation is epsilon is equal to epsilon 0 K. Then our final equation becomes CD is equal to A epsilon 0 K by D. So that is the effect of dielectric on capacitors.